In this video, I'll be talking about isobaric or constant pressure ideal gas processes. Isobaric, iso meaning constant, and bar in Greek meaning weight or pressure, so constant pressure processes. In the upper right, we see the ideal gas law, which shows energy equals energy. Energy on the left side term, the absolute pressure times the volume equals the number of moles times the universal gas constant times the absolute temperature. On the left, I always suggest we draw the PV energy state diagram, where the x-axis is volume of the gas and the y-axis is the absolute pressure. And then I think it's always helpful to draw isothermal lines, as shown in blue here. Lines which are constant temperature, also meaning they are constant internal kinetic energy of the atoms or molecules, and also meaning at every point on that line, product of the absolute pressure times the volume is a constant. Now, in this video, I'll be talking about a case where the final volume is less than the initial volume. So the volume is being compressed, the gas is being compressed, and since it's isobaric, constant pressure, both the initial state and the final state are at the same pressure or the same horizontal value as far as pressure goes. And then we're talking only about here a closed system where there is no mass transfer into or out of the system, and where the system has a constant number of moles of this defined gas in a homogeneous volume. Before we go into any equations, I think it's always helpful on this system diagram shown below the PV energy state diagram, we should be able to pretty much define the directionality and kind of a rough magnitude of what's happening for the types of energy that are contained in the system. The first type of energy I think we should always start with is the internal thermal energy due to the kinetic energy of the molecules. And we can look at this directly from the blue isothermal lines. So at the initial volume and initial pressure, we are at a higher temperature, we are on a higher isothermal line than at the final pressure. So it was compressed, and you can see the temperature dropped. The temperature dropped, and why did the temperature drop? It's because the internal kinetic energy of the molecules dropped. Since the kinetic energy, for example, of a molecule translationally is 1/2 mv squared, kinetic energy dropped, mass remained the same, therefore the velocity dropped. The velocity dropped, it got colder. It got colder, it has less internal energy. So the internal thermal energy at the final state is less than the initial state. So therefore I know the delta U is less than 0. So I have an arrow going down, a blue arrow going down in my system energy state closed system diagram down below to help me to know that the internal energy went down. And we think about, back to the analogy of the checking account, at the end state, there's less money in your checking account than there was at the beginning. So the net change was that there was a loss in internal energy. The next thing we can pretty much always do right away without doing any equations is understand what happened to the work. So first of all, maybe just kind of think about if you've ever had a hand tire pump and you're going from a state where the piston's up high and the plunger's up high and you have high internal volume, and then you compress it and the volume goes down, you as a person are putting work as far as force and displacement into this closed system of gas. So work is going in. Another way to think about it is, so anytime a gas is being compressed, we know that work had to go into it. So you can see the black arrow, I'm showing work is going into the system because I'm compressing. If the opposite happens, if the final volume is greater than the initial volume, then work is going out of the gas system into the surroundings at the transitional boundary. So the black arrow I'm showing going at the interface, work is going into the system. And typically I just talked about having those suffixes. So I describe work out. So if work in is going in, then work in would be positive and work out would be negative. But just the arrow alone kind of tells you that work is going into the system because it's being compressed. So again, back to our analogy of the checking account, at the final time, my balance is less than at an initial state because delta U went down. So there's a net money loss out of the system. And yet from the work, we see that the black arrow work is coming in, or for example, money is coming in. So I have less money at the final state, the initial state, and yet stuff was coming in. So money was being deposited. Yet I ended up losing. And the only way that can happen is for some reason, something went out of the system greater that makes up for the fact that work came in. So that I end up with still a net loss. So in the money terms, something very large, essentially the sum of the work in and the loss, had to come out of the system in order for this to balance. So you have less money at the end, yet you put money in during that time period. You must have taken a lot more money out than the other one. So we know, and for energy, for a closed system, we only have three types of energy. We have internal kinetic energy during the thermal, we have work, the other one is heat. So that means that in our diagram, there had to be a lot of heat that went out of the system in the transitional state from the initial state to the final state. And so therefore, and that loss of heat had to equal the sum of the work that went in and the loss in internal energy. So therefore, you can see that yellow arrow is equal in magnitude to the sum of the other two energy terms. And so therefore, you can see that the heat out was positive. And normally we describe for systems, we talk about heat in. So therefore, the heat in terms of energy had to be negative. So you can do that sort of diagram as far as energy balances on this closed system before you even start any equation work. And then you can do your equations and you can check at the end, is the sign, does it make sense? Do the magnitudes add up right? And is the sign in the right direction that you have an initial impression of how the system should work? For the isobaric compressive process shown, the final state F has less internal thermal kinetic energy than initial state I. In equation form, we can see that the final internal thermal energy is less than the initial internal kinetic energy, so delta U is less than 0. Using the ideal gas assumption, the change in the internal thermal kinetic energy, delta U, is always equal to N, where N is the number of moles, times the molar specific heat at constant volume, which I'm showing as C sub V, which typically has units in the SI system of joule per mole K, which is the same units as R, the universal gas constant, times the temperature in the final state minus the temperature in the initial state, or the delta T. And then uniquely for this isobaric constant pressure process, there's a unique definition of the energy in terms of heat into the system being equal to the number of moles N times the molar specific heat at constant pressure. You can see this sub P, and this system process we're seeing is at constant pressure. So it's going from the initial state I to the final state F. We're following a path along that dashed red line in the PV diagram, which going from the state where at every intermediate state we're at a constant pressure. So therefore, the molar specific heat at constant pressure, C sub P, comes into play only for this constant pressure process. And so therefore, energy in terms of heat into the system is this N times the molar specific heat at constant pressure, C sub P, times the delta T, which is the final temperature minus the initial temperature. It's helpful now to do a check on the signs. So we know that the delta T, the T final minus the T initial, is negative, which would make the energy in terms of heat in to be also a negative. Looking down to the left, we can see that our initial assumption, we were showing that energy in terms of heat was going out of the system, also making the energy in terms of heat in being negative. So we see an agreement between the yellow arrow showing heat in being less than 0 and what our equation says. Considering now the conservation of energy and our energy balance equation for this closed system, which is not accelerating, we know that the delta U, the change in internal kinetic thermal energy, is always equal to energy in terms of heat into the system minus energy in terms of work out of the system. We have solved previously for delta U and Q in, so we can rearrange that equation to solve for work out net. And now we can substitute in the equations for the heat energy in terms of heat in and the energy in terms of the delta U terms as shown. Doing some algebra, we see that we can now define the work out net as N, the number of moles, times the molar specific heat at constant pressure minus the molar specific heat at constant volume, C sub V, times the delta T. And since we're assuming this is an ideal gas, we know that the molar specific heat at constant pressure, C sub P, is always greater than the molar specific heat at constant volume, C sub V, and that difference is the universal gas constant. So molar specific heat, C sub P, equals the molar specific heat, C sub V, plus the ideal gas constant. And therefore, the ideal gas constant R is the molar specific heat at constant pressure, C sub P, minus the molar specific heat at constant volume. So we can substitute R in for that difference in molar specific heat and have an equation now for the workout net. And looking now at the PV energy state diagram, we know that the final temperature is less than initial temperature, therefore delta T is negative. Therefore, N times R times this negative term is also negative, so the workout net is negative. And looking back to our energy state diagram, which we did initially, we were showing that work was going in, as shown by the black arrow going in. So work in was positive, work out was negative, and that's an agreement with the equation we're getting, which also shows that the work out is negative. Another way to directly calculate the work out of the system is the integrated quantity under the pressure value going from the initial volume to the final volume, as shown in the PV energy state diagram in the gray area. So this was a constant pressure system, and we know that the path from the initial to the final states, that work depends on the path, and we're showing that the path is following this dashed red line in the as far as absolute pressure going from this initial volume to the final volume, and the final volume is less than the initial volume, so we know that work out of the system is negative, or work is going into the system. We can solve this work as the integral of the pressure dV from the initial volume to the final volume. And for this one unique case where the pressure is constant, it's isobaric. Pressure is constant, therefore it can be taken out of the integral and essentially end up with P, the integral of the volume from the initial volume to the final volume. From the ideal gas law, we have the variables P, absolute pressure, the variable volume, the variable N, the number of moles, and the variable T. In this case, we know that N is a constant because we defined our system. So we have three variables, the absolute pressure, volume, and temperature. And you can use the ideal gas law to rearrange these variables to solve for whichever you like. And so there on the lower left, we can, for this isobaric process, we can use the ideal gas law to use this equation to, on the left side, it's the differential temperature. The temperature from the final state minus the temperature initial state is the term shown on the right. Now substituting this back into the workout, we can see we get the same workout using the integral as we did the workout when we did the energy balance equation. And therefore, using the equations with this isobaric constant pressure process, we can see that delta U is proportional to the term N, the number of moles, and the delta T term. We can also see down below that the energy in terms of heat in is also proportional to N, the number of moles, and the same delta T term. And on the bottom, we can see that the work out is also proportional to N times the delta T term. So all three energy terms are proportional to N times the delta T term. How we can see that the delta U term in the equation has the molar specific heat C sub V. The energy terms as far as Q in is proportional to the molar specific heat at constant pressure, C sub P. And the energy term with respect to work out is proportional to R, the universal gas constant. And since we know for any ideal gas, the molar specific heat at constant volume, C sub V, is always greater than 1, we know that the delta U term has to be greater in magnitude than the work out term, which is proportional to R. And we also know that the molar specific heat at constant pressure, C sub P, is greater than the molar specific heat at constant volume, C sub V, by the universal gas constant R. And now going back to our energy state diagram, we can see that energy in terms of heat, Q, is the longest arrow. Energy in terms of the delta internal kinetic energy, the blue term, is the medium arrow as far as length. And energy in terms of work, the black arrow, is the shortest arrow. And the proportional length of those arrows are determined by R, the universal gas constant, the molar specific heat at constant volume, C sub V, and the molar specific heat at constant pressure, C sub P.